The universe we see today, filled with galaxies, planets, and endless mysteries, started with something far simpler, the first stars. But what were they really like? These ancient giants, born from the raw ingredients of the cosmos, hold secrets that could rewrite everything we know about the beginning of everything. And here's the wild part: scientists still don't fully agree on how they formed, what they looked like, or even how they died. Some say they were monstrous, others believe they were unlike anything we've ever seen, and a few theories suggest they might still be out there, hiding in plain sight. Today, we're diving into 30 of the most mind-bending theories about these cosmic pioneers, ideas so strange, so revolutionary, they'll make you question the very fabric of reality. Ready to unravel the universe's oldest mystery? Let's begin. The first stars in the universe weren't just ordinary stars, they were unlike anything we see today. Scientists call them population 3 stars, and they were the true pioneers of the cosmos. Born from nothing but hydrogen and helium, these colossal giants formed in the wake of the Big Bang, when the universe was still a dark, empty canvas. Without even a speck of metal, those heavier elements we take for granted now, they burned hotter, brighter, and died faster than any star since. Some may have been hundreds of times more massive than our Sun, shining with such intensity that they could have outshone entire galaxies for their brief, brilliant existence. But their deaths were just as important as their lives. When these titanic stars exploded, they didn't just vanish. They scattered the very first heavier elements into space, from carbon to oxygen and beyond. Those elements became the building blocks for everything that followed: new stars, planets, and eventually us. So in a way, every atom in your body once passed through the heart of one of these ancient, long-vanished giants. Poetic, isn't it? Now, imagine looking up at a night sky filled with these monstrous stars, no planets, no galaxies, just raw, untamed light. That was the universe in its earliest days. Finding traces of the very first stars might sound impossible after all. They lived and died over 13 billion years ago. But astronomers aren't giving up. Their game plan: look for the ghosts of these ancient giants. When population 3 stars exploded, they didn't just vanish, they left behind fingerprints. Maybe in the form of distant light echoes, faint chemical signatures in the oldest galaxies, or even black holes still lingering from their violent deaths. The James Webb Space Telescope is our best shot at spotting them. With its infrared eyes, JWST can peer back further than any telescope before, searching for the unique glow of those primordial stars or the unusual way they altered their surroundings. Why does this matter? Because finding even one would be like uncovering the Rosetta Stone of the cosmos, proof of how the first structures in the universe took shape. It could settle debates about star formation in the early universe, reveal how quickly heavy elements spread, and maybe even rewrite the timeline of cosmic dawn. Every flicker of light from that era carries a message, and we're finally learning how to listen. Here's one of the most fascinating twists in the story of the first stars: dark matter may have been their silent midwife. We often think of dark matter as this mysterious, invisible presence, but what if it played a crucial role in lighting up the universe? Some scientists believe its gravitational pull acted like cosmic scaffolding, shaping the sparse gas clouds of the early cosmos into dense knots where stars could ignite. Without dark matter's subtle guidance, those primordial hydrogen and helium clouds might have remained too spread out, delaying the birth of the first stars for eons. Cutting-edge simulations back this up. They show dark matter's gravity creating dense pockets where gas could collapse faster, triggering star formation in a universe barely 100 million years old. Imagine that, an invisible force sculpting the first beacons of light in the cosmos. It's a humbling reminder that even the earliest stars didn't form alone, they had help from the shadows. What if the first stars weren't just giants but absolute cosmic behemoths? Picture a star so massive it makes our sun look like a speck of dust. Some theories suggest the earliest stars could have weighed in at thousands of times the mass of the Sun, burning furiously bright before collapsing into black holes that would dominate the young universe. These supermassive stars weren't just anomalies, they may have been the architects of everything we see today. Born in the densest pockets of the primordial universe, they lived fast, burned hot, and died young. But their deaths weren't the end. Instead, they collapsed into black holes so massive that they became the seeds of the very first galaxies. These black holes, some of the universe's first, could have pulled in surrounding gas, triggering the birth of new stars while shaping the structure of entire galaxies. It's a staggering thought. The supermassive black holes we now see at the centers of galaxies, including our own Milky Way, might trace their origins back to these fleeting titanic stars. So the next time you hear about a distant quasar or a galaxy's mysterious core, remember, you might be glimpsing the legacy of a star so powerful it helped build the cosmos. We often picture the first stars as lonely titans blazing in the darkness, but what if they weren't alone at all? Recent research suggests some of these ancient giants might have formed in pairs or even small clusters, rewriting our understanding of the early cosmos. Think about it. Today, most massive stars we observe have stellar companions, so why wouldn't the first stars follow the same rules? Advanced simulations now show that collapsing gas clouds in the early universe could have split into multiple fragments, birthing binary or even triple star systems. These cosmic siblings would have shaped each other's destinies, swapping material, distorting each other's gravity, and potentially cutting their lives short through dramatic collisions. And here's the real kicker. If these stars were born together, their deaths would have scattered heavy elements across wider regions, seeding the universe with ingredients for future stars and planets far more efficiently than a single explosion could. That means the very chemistry of our cosmos and even the building blocks of life may owe itself to these primordial stellar duos. So the next time you gaze up at the stars, remember, the universe's first light might not have been a solo act but a spectacular cosmic dance. For decades, we assumed the universe's first stars were all solitary giants, colossal, short-lived beacons burning in isolation. But nature has a way of defying expectations. Cutting-edge simulations reveal something startling. Those primordial gas clouds might not have birthed just single massive stars. Instead, turbulence and chaotic motions within the collapsing hydrogen and helium could have fractured them like a spinning droplet splitting apart. This means some of the earliest stars might actually have been smaller, maybe dozens or even hundreds of times the Sun's mass instead of thousands. Don't get me wrong, that's still enormous by today's standards, but it changes everything. If true, these fragmented stars would have behaved differently, burning longer, dying less violently, and enriching their surroundings with heavy elements more gradually. Some could have even survived long enough to witness the birth of the second generation of stars, bridging cosmic epochs. It's a subtle twist, but think about the implications. Rather than a sky dominated by rare, monstrous titans, the early universe might have twinkled with a diverse population of stars, some large, some relatively small, each playing a unique role in shaping the cosmos. Suddenly, the story isn't just about brute force, but complexity arising from chaos. And that makes the dawn of the universe far more interesting than we ever imagined. One of the greatest puzzles in astronomy isn't just about understanding the first stars, it's about why we can't seem to find them. If these colossal giants once dominated the early universe, where's the proof? The challenge comes down to distance and time. We're trying to spot stars that lived over 13 billion years ago, whose light has stretched into faint infrared whispers by the time it reaches us. Even with telescopes like JWST pushing the limits, catching their glow is like searching for a single candle flickering at the edge of the observable universe. But what if the reason goes deeper? Some theorists propose these stars didn't just fade, they vanished. Imagine a star so massive that after burning furiously for just a few million years, it collapsed straight into a black hole, leaving almost no trace behind. No explosive supernova, no glittering nebula, just an invisible sinkhole in space. Others speculate these stars might have been shrouded in thick cocoons of primordial gas, dimming their light before it could escape. Or perhaps they're hiding in plain sight, their signatures blended into the glow of younger galaxies. Every dead end in this search forces us to rethink what we know about cosmic dawn. Maybe the stars didn't play by the rules we expect, and that's what makes hunting them so thrilling. The absence of evidence isn't just a setback, it's a clue that the early universe was far stranger than we've dared to imagine. Picture this: a star unlike any other, powered not just by nuclear fusion, but by the annihilation of dark matter itself. One of the most radical theories about the first stars suggests they may have been cosmic hybrids, fueled by both ordinary matter and the mysterious invisible substance that makes up most of the universe's mass. Here's how it could work. In the dense early universe, dark matter may have clumped together at the hearts of these primordial stars. As particles of dark matter collided, they would annihilate on contact, releasing bursts of energy that could have supercharged the star from within. This wouldn't just make the star burn brighter, it might have dramatically extended its lifespan. Normally, supermassive stars live fast and die young, collapsing within a few million years. But with dark matter constantly feeding them energy, they could have stabilized, burning slower and lasting far longer than physics would normally allow. Some models even suggest these stars might still exist today, lurking in the cores of galaxies where dark matter is densest, hidden relics of the universe's infancy. If true, this would mean the first stars weren't just celestial objects, they were cosmic laboratories, testing the fundamental laws of physics in ways we're only beginning to grasp. The implications are staggering. If dark matter really did shape the lives of the earliest stars, then its fingerprints might be written across the entire history of the cosmos. Now, let's take things up a cosmic notch with one of the wildest ideas about the first stars, or rather, what they might have become. Picture a celestial monster so bizarre it blurs the line between star and black hole. Enter the quasi-star, a hypothetical beast that could rewrite the rules of early cosmic evolution. Imagine a star not just hundreds but millions of times the mass of our Sun, swollen to unimaginable proportions. But here's the twist: instead of a typical stellar core, this thing harbored a black hole right at its heart, not as a killer but as an engine. As gas from the star's outer layers spiraled inward, feeding the black hole, the energy released could have kept the star puffed up like a balloon, glowing brilliantly for thousands of years. It's like a cosmic balancing act, gravity trying to crush it, while the black hole's appetite keeps it inflated. These quasi-stars wouldn't have just been oddities, they might have been the universe's first factories for supermassive black holes. By the time the outer layers finally dissipated, the black hole inside could have already grown to a staggering size, seeding the early galaxies we see today. Think about that. The dark hearts of galaxies like our own Milky Way might trace back to these titanic, short-lived hybrids. If they existed, they were the ultimate transformers, neither fully star nor fully black hole, but something entirely new, sculpting the cosmos in ways we're only beginning to untangle. We think of the early universe as a place of raw chaos, hot, dense, and lawless. But what if hidden forces were quietly shaping its evolution? Enter one of the most overlooked players in cosmic history: magnetic fields. Even in those first moments after the Big Bang, weak magnetic threads may have woven through the fabric of space, subtly guiding the birth of the first stars. Picture a delicate spider's web, invisible to the eye, yet strong enough to redirect the flow of gas and dust. These faint magnetic forces could have steered collapsing clouds of hydrogen and helium, determining whether a star grew into a solitary giant or fractured into smaller siblings. Simulations now reveal that even a field billions of times weaker than Earth's own magnetism might have been enough to tip the scales, preventing runaway growth in some regions while accelerating it in others. That means the sizes of the first stars and even the distances between them might not have been random at all. They could have been orchestrated by whispers of magnetism we're only now learning to detect. It's a humbling thought. The universe's earliest light may have flickered to life not just through gravity's brute force, but under the gentle pull of a cosmic current we're still struggling to measure. Here's where things get truly mind-bending. What if the seeds of the first stars were planted before stars even existed? Rewind to the universe's first split second, when an explosive growth spurt called cosmic inflation stretched space itself faster than light. During that unimaginable expansion, tiny quantum ripples, random flickers at the smallest scales, got stretched into cosmic scale wrinkles. These ripples became the blueprint for everything: galaxies, galaxy clusters, and yes, even the distribution of the very first stars. Imagine tossing pebbles into a pond, then suddenly stretching that pond to the size of an ocean. The ripples would freeze into vast, gentle waves. That's essentially what inflation did to those early quantum fluctuations. Fast forward a few 100 million years, and those subtle density variations guided where gas would clump, determining which regions birthed monstrous stars and which remained empty. The wildest part, we might still see traces of this today. The uneven distribution of ancient starlight, the way early galaxies cluster, these could all be echoes of quantum physics magnified to cosmic proportions. So when we study the first stars, we're not just looking at ancient objects, we're glimpsing the fingerprints of the universe's very first moments. That's the real magic here. The biggest structures we know might owe their existence to the tiniest fluctuations imaginable. Now let's talk about something truly elusive: particles that might not even exist, yet could rewrite the story of the first stars. Meet sterile neutrinos, the ghostly cosmic wildcards. Unlike ordinary neutrinos, which barely interact with matter, sterile neutrinos, if they're real, would be even more aloof, slipping through the universe like silent shadows. But here's the twist: their very detachment could have had a chilling effect on the early cosmos. Picture this: primordial gas clouds, hot and turbulent, ready to collapse into stars. But if sterile neutrinos were drifting through, they might have acted like tiny heat sinks, sapping energy from those gases and cooling them faster than expected. Why does that matter? Because cooler gas collapses more easily, meaning stars could have formed earlier, smaller, and in greater numbers than we thought. Some models suggest this cooling effect might have even prevented the birth of those supermassive monster stars, instead favoring a universe filled with slightly smaller, but still enormous, stellar pioneers. It's a cosmic ripple effect, one tiny hypothetical particle altering the timeline of light itself. And if future experiments ever confirm sterile neutrinos exist, we might have to rethink not just the first stars, but the entire recipe for how structure emerges in the universe. The lesson: sometimes the biggest cosmic shifts come from the things we can't even see. What if everything we've assumed about the first stars is wrong? Buckle up, because there's a radical idea bubbling at the edges of cosmology, one that flips the script entirely. Some theorists argue the universe's earliest light didn't come from stars at all. Instead, they propose a darker, stranger alternative: black holes forming directly from collapsing gas, no stars required. Here's how it could have happened. Picture the primordial cosmos, a sea of hydrogen and helium, but with pockets so dense and turbulent that gas didn't gently coalesce into stars. It imploded violently under its own weight, skipping the stellar phase altogether. These black holes wouldn't just be cosmic dead ends, they could have been the universe's first powerhouses. Swallowing surrounding matter, they might have unleashed jets of energy so intense they mimicked starlight, jump-starting galaxy formation without a single traditional star in sight. Critics argue this challenges too much of what we observe, like the spread of heavy elements we know came from stars. But supporters counter that under extreme early conditions, physics might have played by different rules, rules where black holes were the universe's first architects, not its tombstones. It's a dizzying thought. The dawn of light might not have been gentle at all, but a scream of radiation from the birth of something far more enigmatic. Among all the explosions in the cosmos, none match the raw, apocalyptic power of gamma-ray bursts, brief flashes so intense they outshine entire galaxies. And here's the startling connection. The deaths of the first stars may have been the ultimate source of these cosmic detonations. When a population 3 star reached the end of its short, furious life, it didn't just fade away, it likely exploded with a violence we can barely fathom. Picture a star hundreds of times more massive than our Sun, its core collapsing into a black hole while the outer layers detonated in a supernova so powerful it unleashed a focused beam of gamma radiation across the universe. These beams, narrow and deadly, could have sliced through the early cosmos like cosmic lasers, leaving behind the brightest flashes ever recorded. Even more intriguing, some models suggest these bursts might have been thousands of times more energetic than the gamma-ray bursts we observe today, fueled by the sheer mass and pristine composition of the first stars. That means if one erupted nearby today, it could strip Earth's ozone layer in seconds. But in the early universe, these explosions weren't just destructive, they were transformative. The intense radiation may have ionized vast regions of space, clearing the fog of primordial gas and paving the way for future galaxies. So the next time astronomers spot a distant gamma-ray burst, they might be witnessing the final, fading echo of a star that helped shape the universe itself. The universe's first stars might have had silent partners, ones we'd never see coming. Imagine a swarm of primordial black holes, no bigger than mountains but packing the mass of entire planets, left over from the chaos of the Big Bang. These ancient relics could have lurked in the darkness, their gravity subtly tugging at clouds of hydrogen and helium, coaxing them to collapse faster than they ever would alone. Here's the twist. While normal star formation relies on gas slowly gathering over millions of years, these tiny black holes might have acted like cosmic shortcuts, creating dense knots of matter where stars could ignite almost overnight. Think of them as invisible seeds planted in the fabric of space itself, sprouting the universe's first light. And if they existed, their influence wouldn't have stopped there. These black holes could have altered the sizes and lifespans of those early stars, making them burn hotter, die younger, or even skip certain phases entirely. The craziest part, some of these primordial black holes might still be drifting through the cosmos today, hidden and untouched, carrying secrets about how the first stars were born. So the next time you hear about mysterious gravitational signals or unexplained cosmic structures, remember, we might be seeing echoes of the universe's original starlight, sculpted by shadows we've yet to fully discover. Here's where the chemistry of the early universe throws us a curveball. Before stars could ignite, something had to cool things down. Without metals or dust to radiate heat away, those primordial gas clouds should have stayed too hot and puffed up to collapse. So how did the first stars ever form? The answer lies with a simple but powerful molecule, molecular hydrogen. Just 2 hydrogen atoms bound together, yet this tiny duo became the universe's first cosmic air conditioner. As dense pockets of gas began contracting, molecular hydrogen acted like a heat sink, absorbing energy from collisions and then re-radiating it away as infrared light. This process bled off just enough warmth to let gravity take over, squeezing the gas tighter until ignition. Think of it like steam escaping a boiling kettle, slowly lowering the pressure inside and allowing collapse. Without this cooling effect, those clouds might have remained too energetic, bouncing apart instead of forming stars. The real kicker, this mechanism worked because the early universe lacked metals. Heavier elements would have cooled the gas too efficiently, potentially fragmenting it into smaller stars. But molecular hydrogen struck the perfect balance, just enough cooling to birth massive stars, but not so much that it splintered them into countless tiny ones. It's a delicate dance of physics that shaped the entire trajectory of cosmic dawn. So when we marvel at the first stars, we're really celebrating the quiet power of a molecule so humble, it's easy to overlook, but without it, the universe might have stayed dark forever. The universe's first stars didn't just appear randomly. They were born along hidden highways of dark matter, stretching like cosmic spiderwebs across the emptiness. Modern supercomputer simulations reveal something breathtaking. The early universe wasn't a formless void, but a delicate lattice of dark matter filaments, invisible threads weaving through space. And where these filaments crossed, gravity worked its magic, pulling together the sparse hydrogen and helium into dense knots, perfect nurseries for the first stars. Picture it like dew collecting on a spider's web at dawn. Those gossamer strands of dark matter, though invisible, created tiny pockets where gas could pool and ignite. The stars didn't form in isolation. They lined up like beads on a string, following the hidden architecture of the cosmos. Some of these filaments stretched for millions of light years, with stars flickering to life at their intersections, marking the universe's first large-scale structure. What's even more astonishing, these same filamentary blueprints still shape the universe today. Galaxies cluster along them, drawn by gravity's unseen hand, proving the ancient scaffolding never really vanished. It just became harder to see beneath the dazzling lights of modern stars. So when scientists map the cosmic web in our current universe, they might actually be glimpsing the ghostly remains of the very framework that gave birth to the first starlight. It's a humbling thought. The universe's greatest structures were set in motion before the first star ever shone. For all our talk about the first stars blazing to life in the universe's infancy, there's a quiet but compelling counterargument brewing among astronomers. What if we've been too eager to declare when cosmic dawn truly began? A growing faction of researchers suggests star formation might have kicked off significantly later than traditional models predict, potentially rewriting our understanding of the universe's early chapters. Here's the puzzle. If the first stars ignited as early as we think, their ultraviolet light should have ripped electrons from surrounding hydrogen atoms in an epic process called reionization. Yet recent observations of this cosmic milestone don't quite align with that timeline. Some simulations now show primordial gas clouds may have stubbornly resisted collapse for an extra 100 million years or more, held back by turbulence, weak gravitational pulls, or even the cooling inefficiency of pure hydrogen and helium. Delayed star formation wouldn't just tweak a timeline, it could reshape how we see the universe's entire transformation from darkness to light. Pushing back the birth of the first stars means the era of reionization might have been more abrupt, with galaxies playing a bigger role than isolated stellar giants in clearing the cosmic fog. It's a subtle shift with massive implications. If true, the universe's opening act wasn't a solo performance by colossal stars, but an ensemble piece where timing changed everything. Suddenly, the cosmos's childhood looks far less predictable, and that's what makes this debate so thrilling. Here's one of the cosmos' quietest mysteries. Why is there so little lithium in the oldest stars? It sounds like a niche puzzle, but it's actually a glaring clue about the universe's first starlight. According to Big Bang nucleosynthesis, the early universe should have left behind trace amounts of lithium, and for a while, astronomers assumed it was all neatly tucked into ancient stars. But when they checked, the numbers didn't add up. Some of the most pristine stars, relics from near cosmic dawn, have less lithium than predicted. Something or someone was stealing it. The prime suspect, those first-generation stars. Here's the twist. As those massive, short-lived giants burned through their fuel, their internal convection may have dragged lithium down into their searing cores, where temperatures were high enough to destroy it. Think of it like a cosmic blender. Once lithium got pulled deep enough, it was game over. But there's another possibility. The violent deaths of these stars could have unleashed floods of radiation, shredding lithium atoms in surrounding gas before they could ever get baked into the next stellar generation. This isn't just about one missing element, though. The lithium problem forces us to rethink how those first stars lived and died, whether they were more efficient destroyers than we imagined, or if their explosions reshaped the chemistry of the early universe in ways models still struggle to explain. Solving it could give us a clearer snapshot of cosmic dawn, not just when the lights turned on, but what those first flames truly burned away. Imagine trying to light a candle in a room filled with thick fog. The flame struggles to shine through, just as the universe's first starlight might have fought against an invisible cosmic barrier. This is the opaque universe challenge, a puzzle that suggests early star formation wasn't just about gravity pulling gas together. It was a battle against light itself. In those first 100 million years, the cosmos was crammed with free electrons, remnants of the Big Bang's searing heat. These particles scattered photons like bumper cars, trapping light and turning the universe into a hazy, glowing plasma. For stars to form, gas had to cool enough to collapse, but with photons constantly bouncing around, heat couldn't escape efficiently. It's like trying to chill a pot of soup while the lid is locked shut. Without cooling, those primordial gas clouds stayed puffed up, delaying star birth until the universe expanded enough to thin the electron fog. Here's the turning point. As space stretched, electrons finally paired up with protons, forming neutral hydrogen and clearing the cosmic mist. Only then could infrared light emitted by molecular hydrogen escape, allowing gas clouds to shed heat and crumple into stars. It's a delicate timing issue: too early, and the universe's opacity smothers star formation; too late, and galaxies might not have had time to assemble. This theory flips the script on cosmic dawn, suggesting the first stars didn't just flicker on when gravity allowed it, but when the universe itself finally became transparent enough to let them shine. The implications are profound. If the opaque universe theory holds, it means the earliest stars didn't just depend on their own physics. They were at the mercy of the cosmos' evolving structure. Their birth wasn't just a local event. It was synced to the universe's grand transition from a glowing plasma to a star-studded sky, and that changes how we search for them today. Instead of scanning for starlight from the very beginning, we might need to focus on the moment when the cosmic fog lifted, revealing a universe finally ready to spark its first flames. When we think of planets, we imagine worlds rich in silicon, iron, and carbon, ingredients that simply didn't exist before the first stars forged them. But what if those very stars, in their explosive final acts, laid the groundwork for the earliest solid bodies in the cosmos? Here's the tantalizing possibility. When a population 3-star reached the end of its brief, fiery life, its death throes didn't just scatter atoms, they might have forged microscopic dust grains, the seeds of future planets. Even without today's abundance of heavy elements, shockwaves from these supernovae could have crushed carbon and silicon atoms together, creating tiny diamond-like crystals or sand-like particles. Picture it: a blizzard of stardust, each speck a potential building block. But how could these flecks grow into anything substantial? Gravity in the early universe worked differently. In the dense wakes of stellar explosions, debris might have clumped faster than we'd expect, with electrostatic forces helping particles stick like cosmic Velcro. Some models suggest these protoplanetary rubbles could have reached kilometer sizes before proper metals even existed, forming bizarre, rocky bodies made of minerals we'd barely recognize today. The real twist: these early planets wouldn't have orbited stars, they might have drifted freely through space, relics of stellar violence waiting to be captured by newborn galaxies. If so, the universe's first solid worlds weren't gentle, life-friendly places. They were ash-born wanderers, forged in fire and cast adrift, proof that even in chaos, the cosmos was already assembling the pieces of something greater. Picture a universe where dark matter isn't just an invisible presence, it's a cosmic fluid, rippling with waves so vast they could cradle entire galaxies. That's the radical premise of fuzzy dark matter, a theory suggesting the mysterious substance isn't made of heavy, sluggish particles, but of feather-light ones billions of times less massive than electrons. If true, these particles would behave less like scattered rocks and more like an ocean, their quantum waves stretching across light years, gently sculpting the cosmos. How does this change the story of the first stars? Instead of dark matter clumping into dense halos, these wave-like ripples would have created a delicate interference pattern, zones of higher and lower density like the peaks and troughs of a sound wave. Gas clouds in the early universe wouldn't just collapse randomly. They'd follow this hidden rhythm, pooling where the waves aligned to deepen gravity's pull. The result, stars might have ignited in sprawling, web-like patterns, with vast empty spaces between them like fireflies blinking to life on the crests of an invisible tide. Here's where it gets even stranger, because fuzzy dark matter's waves are so enormous, they could have suppressed the formation of tiny, early structures entirely. No dwarf galaxies forming first, no small-scale clumps, just a smooth, gradual build-up toward larger stars and galaxies. That might explain why some simulations struggle to replicate the universe's small-scale structures. If dark matter truly is fuzzy, its waves could have ironed out the cosmic wrinkles we expect to see. The echoes of this might still be visible today. If the first stars were born along these ghostly wavefronts, their descendants, ancient star clusters or oddly spaced dwarf galaxies, could still carry the imprint of dark matter's quantum origins. It's a breathtaking idea. The universe's first light didn't just pierce the darkness, it danced to the silent tune of waves we're only now learning to imagine. Some of the universe's most energetic particles might trace their origins back to the explosive deaths of its first stars. When those colossal population 3 stars reached the end of their brief lives, they didn't just fade away. They detonated with enough force to rip apart the fabric of space itself. These supernovae weren't just cosmic fireworks, they were particle accelerators on a galactic scale, hurling matter outward at nearly the speed of light. The shockwaves from these blasts could have sent protons and atomic nuclei careening across the early universe, creating the very first cosmic rays, high-energy visitors that still rain down on Earth today. What makes this remarkable isn't just the raw power involved, but the timing. These explosions happened in a universe that was still largely pristine, free from the tangled magnetic fields and dust that slow and scatter cosmic rays today. That means particles from those first supernovae might have traveled farther and faster than anything since, seeding the cosmos with an invisible rain of energy that could have influenced everything from galaxy formation to the chemistry of early gas clouds. Here's the wild part, some of these ancient cosmic rays might still be out there. While most would have long since dissipated, simulations suggest a few could have journeyed for billions of years, their paths bent by gravity but their energy undiminished. If we could trace one back to its source, it might point directly to the corpse of one of those primordial giants, a cosmic message in a bottle from the universe's fiery youth. Yet the real legacy of these particles isn't just in their endurance, it's in what they triggered. As they slammed into clouds of hydrogen and helium, they could have knocked electrons loose, ionizing gas and jump-starting new rounds of star formation in regions that might otherwise have remained dormant. In a way, those first cosmic rays weren't just debris, they were the matchsticks that helped light the next generation of stars, proving that even in death, the universe's first luminaries shaped everything that followed. Among the most haunting possibilities about the first stars is this: some may have vanished without a trace, not with a bang but with barely a whisper. While we often picture these ancient giants meeting violent ends as supernovae, tearing themselves apart in spectacular explosions, there's a growing case for a far quieter fate. Imagine a star so massive, so overwhelmed by its own gravity, that when its fuel ran out, it didn't explode, it simply imploded, vanishing straight into a black hole without fanfare. No blinding flash, no shockwave rippling through space, just an eerie silence where a star once burned. This no supernova scenario flips everything we assume about stellar deaths on its head. For stars above a certain mass threshold, perhaps 200 or more times heavier than our Sun, the core's collapse might be too swift, too absolute for any outer layers to rebound into an explosion. Instead, the entire star gets swallowed by its own crushing gravity, as if space itself simply reached up and erased it. No heavy elements scattered into the void, no brilliant light to echo across billions of years, just an invisible tombstone drifting in the dark. Here's why this matters. If even a fraction of the first stars died this way, our search for their remnants just got infinitely harder. Traditional methods like hunting for the chemical fingerprints of supernova in ancient gas clouds would come up empty. These silent collapses would leave behind black holes with no surrounding debris, no telltale glow from heated ejecta. The only traces might be subtle gravitational ripples, warps in spacetime too faint for current telescopes to spot. Yet there's a tantalizing clue hidden in the cosmos's quiet corners. Some of the oldest, most massive black holes we've detected, those lurking in distant galaxies far earlier than expected, could be the descendants of these vanished stars. Their very existence hints at a population of first-generation black holes born not from explosions but from utter collapse. If true, it means the universe's earliest stars didn't just blaze and fade. Some may have stepped off the cosmic stage without a sound, leaving behind only shadows we're still learning how to see. Now let's turn to one of the most transformative periods in cosmic history, the epoch of reionization, and how the first stars played a starring role in this grand celestial overhaul. Picture the early universe as a dense, murky fog of hydrogen gas, its atoms so tightly packed that light couldn't travel far without scattering. But then came the ultraviolet fury of those primordial stars, blazing through the darkness like cosmic blowtorches. Their intense radiation didn't just illuminate the void. It ripped electrons straight off hydrogen atoms, stripping them down to bare protons in a process as violent as it was necessary. This wasn't just a minor tweak, it was a universal renovation. Before reionization, the cosmos was opaque, its hydrogen gas soaking up starlight like a sponge. But once those first stars got to work, their UV photons punched through the fog, carving out bubbles of transparency that eventually merged, turning the entire universe into the crystalline expanse we see today. Think of it like thawing frost off a window pane, one patch at a time, until finally, light could shine unobstructed across billions of light years. But here's the puzzle: did these stars act alone? Recent observations suggest reionization might have been messier than we thought. A stop-and-start process where some regions cleared early while others lagged behind. That inconsistency hints at something deeper. Perhaps the first stars weren't evenly distributed but clustered in rare, brilliant pockets, their combined light surging outward like shockwaves. Or maybe their black hole remnants took over, with quasars contributing their own torrents of ionizing radiation. The stakes couldn't be higher. If we can map how reionization unfolded, when it began, how quickly it progressed, we'll unlock clues about the first stars' sizes, lifespans, and even their deaths. Every photon they emitted, every electron they liberated, left an imprint on the fabric of spacetime itself. And now, with telescopes like JWST peering back to this pivotal era, we're closer than ever to reading that cosmic blueprint, one ultraviolet whisper at a time. Here's a cosmic detective story that might change how we see the ancient stars scattered across our galaxy. When astronomers peer into the night sky, hunting for the universe's very first stars, they often focus on the oldest, most metal-poor stars, those pristine relics from near the dawn of time. But what if some of these so-called ancient stars aren't the pioneers we think they are? A fascinating theory suggests we might be getting fooled by an illusion, that some stars we've labeled as primordial are actually the immediate offspring of the true first generation. Think of it like finding a faded photograph from the 1920s, only to realize it's actually a carefully aged reprint from the 1950s. The difference is subtle but critical. When those massive population 3 stars exploded, They scattered their heavy elements into nearby gas clouds, just enough pollution to birth a second wave of stars with barely a whisper of metals. These stars, forged from nearly pristine material but not entirely pure, could easily masquerade as their ancestors, blurring the line between generations. The implications are huge. If we've misidentified even a fraction of these stars, it means our window into cosmic dawn might be smudged. We could be studying slightly contaminated stand-ins while the true first stars remain hidden, either because they died out completely or are simply too faint to spot. Some astrophysicists argue that the only way to find the genuine pioneers is to hunt for stars with absolutely zero heavy elements, a signature so rare it might not even exist anymore. Yet there's a tantalizing alternative. Maybe the first stars didn't pollute their surroundings evenly. In the turbulent early universe, some gas pockets could have stayed untouched by nearby supernova, allowing second-generation stars to form with almost identical chemistry to their parents. That would mean the distinction between generations isn't just hard to spot. It might be invisible, leaving us with a cosmic hall of mirrors where the past is far more elusive than we ever imagined. So next time you hear about an ancient star discovered near the Milky Way's edge, remember, it might not be the original trailblazer, but a near-perfect copy standing in for stars long gone. And that raises the real question. If the universe's first light is playing hide and seek with us, how do we learn to see through the illusion? Now let's venture into one of the most mind-bending frontiers of physics, where gravity itself might have played by different rules in the universe's infancy. At scales smaller than an atom, the familiar pull of gravity we know dissolves into a strange quantum realm where particles flicker in and out of existence, and space-time itself behaves like a turbulent foam. In those first moments after the Big Bang, when matter was unimaginably dense, these quantum fluctuations might not have been mere background noise. They could have rewritten gravity's script entirely. Imagine gravity waxing and waning unpredictably, like a flickering light bulb, as quantum effects twisted its strength from one instant to the next. In such extreme conditions, collapsing gas clouds might have encountered bizarre resistance or unexpected boosts as they tried to form stars. Some regions could have experienced gravity weaker than expected, delaying star birth, while others might have felt a crushing surge accelerating it. The result, a patchwork of stellar formation where timing and location depended on the quantum dice roll of space-time itself. This isn't just wild speculation. Some theories suggest these quantum gravity effects could explain why early stars seem to cluster in ways standard models struggle to predict. If gravity wasn't uniform but instead pulsed in strange subatomic rhythms, it would leave behind an imprint, stars born too early or in odd configurations like footprints in the cosmic sand. The most radical implication: if quantum gravity sculpted the first stars, we might uncover its fingerprints by studying the oldest structures in the sky. Telescopes searching for anomalies in early galaxy distributions, pockets of stars too dense or sparse, could be glimpsing the ghosts of a time when gravity itself was still learning the rules. It's a humbling thought. The universe's first light may have been shaped by forces so subtle, we're only now beginning to suspect they were there at all. What if the first stars didn't just burn brightly in our familiar three-dimensional space, but flickered between dimensions we can't even perceive? String theory, that mind-bending framework suggesting the universe has more hidden dimensions than we experience, might hold the key to one of the wildest twists yet in the story of cosmic dawn. Picture this: in those first moments after the Big Bang, when the fabric of reality was still stretching and settling, extra dimensions, tiny, curled up loops or vast, unseen planes might have influenced how gravity shaped the earliest stars. Here's how it could have worked. In our everyday world, gravity weakens with distance. Drop an apple, and it falls straight down. But in a universe with extra dimensions, gravity might have leaked into those hidden realms, altering its strength on microscopic scales. For collapsing clouds of primordial hydrogen, this could have meant a critical difference. Gas that would have stayed diffuse in 3 dimensions might have crumpled faster with gravity's extra pull, igniting stars sooner, hotter, or even more massive than physics currently allows. Some models suggest these stars wouldn't have been spheres as we know them, but twisted shapes, their light and energy bleeding into dimensions beyond our perception. The implications are staggering. If true, these stars' deaths might have left behind not just black holes, but higher dimensional remnants, cosmic relics lurking just outside our observational reach. Their radiation could have carried signatures of those extra dimensions, imprinting patterns on the early universe's light that we might still detect today. It's like finding fingerprints on a window pane, except the hand that left them exists in a direction we can't point to. Of course, skeptics argue this is all speculative. Without direct proof of extra dimensions, the idea remains a tantalizing what if. But here's the thing. If future telescopes ever spot anomalies in the oldest starlight, odd flickers, unexpected temperature ripples, they might be glimpsing echoes of a multidimensional origin. That's the real thrill here. The first stars might not just illuminate our past, but dimensions we've yet to name. And who knows, maybe the universe's earliest light is still shining somewhere, just not entirely in our world. Among the grand tapestry of the early universe, we've often imagined the first stars blazing to life in crowded stellar nurseries, dense knots of gas where gravity worked overtime. But what if some of these pioneers weren't team players at all? Enter the lone wolf theory, a bold idea suggesting that not all first-generation stars formed in bustling proto-galaxies. Some might have ignited in the cosmic boonies, the vast, empty voids between structures, where only traces of hydrogen and helium drifted in near-total isolation. Picture a single massive star, hundreds of times heavier than our Sun, burning fiercely against the blackness of a void. No neighbors, no galaxy in sight, just raw starlight piercing the darkness. These solitary giants would have lived brief, brilliant lives before exploding in supernova so remote, their light might never have reached another structure. But their legacy wouldn't be in visibility, it'd be in chemistry. Even one such explosion could seed its surrounding void with heavy elements, polluting what should have been pristine emptiness with carbon, oxygen, and iron. Here's where things get intriguing. Astronomers have long assumed the spaces between galaxies were near-perfect vacuums, barely touched by star formation. Yet recent observations reveal whisper-thin traces of metals floating in these voids, elements that shouldn't be there unless something forged them. Lone wolf stars could be the culprits. Their explosions wouldn't just scatter metals, they'd send shockwaves rippling through the void, potentially triggering ripples of density that influenced future galaxy formation in ways we're only starting to map. The kicker: finding proof. Isolated stars this ancient would have died eons ago, leaving no direct light for telescopes to catch. Instead, researchers hunt for their fingerprints, those unexplained metal traces in deep voids, or oddball stars in modern galaxies with chemical signatures hinting they formed in total isolation before being captured. It's a cosmic game of hide and seek where the hiders vanished billions of years ago, and all we have are the echoes they left behind. So next time you think of the early universe, don't just picture crowded stellar cities, remember the outliers, the rebels who lit up the darkness alone. Their lonely fires might have changed the cosmos in ways we're only beginning to measure. The universe may have had an unexpected head start in brewing the ingredients for life, not from stars, but from the violent collisions of their ultra-dense corpses. Long before the first stars illuminated the cosmos, pairs of neutron stars, those city-sized remnants of dead stars could have spiraled together in catastrophic mergers, detonating with enough force to scatter gold, platinum, and uranium across the primordial darkness. This theory flips the script on cosmic chemistry. We've always assumed heavy elements were forged exclusively inside stars or their explosive deaths. But neutron star mergers are element factories on overdrive, capable of producing rare metals in staggering quantities during their collisions. Now imagine these cataclysms happening in a universe barely 100 million years old, seeded by hypothetical population Roman III stars that lived and died in mere cosmic moments. Their neutron star descendants, locked in tight orbits, would have smashed together far sooner than expected, spraying the early cosmos with metals before most stars even had a chance to form. The implications: those first official stars might not have been as pristine as we thought. Instead of birthing from pure hydrogen and helium, some could have condensed from gas subtly laced with traces of heavier elements just enough to alter their physics. Even a whisper of these metals could have cooled gas clouds faster, leading to smaller, longer-lived stars that burned differently than their uncontaminated siblings. It's like adding a pinch of salt to a recipe barely noticeable but enough to change the entire dish. The hunt for proof lies in the oldest stars we've found. Some exhibit bafflingly early traces of heavy elements, as if something enriched their nurseries prematurely. Could neutron star mergers be the culprits? If so, they didn't just set the table for the universe's first stars, they seasoned the cosmic soup before the cooking even began. Now let's tackle a theory so out there, it bends the boundaries of science and philosophy. What if the bizarre behavior of the first stars isn't just astrophysics but evidence we're living in a cosmic simulation? Before you dismiss this as sci-fi, hear the logic. The first stars break nearly every rule we know. Their sizes, lifespans, even the way they formed, like an architect testing extreme conditions in a digital sandbox. Think about it. In a simulation, the earliest iterations often have glitches or oversimplified physics to save processing power. Could the first star's strange properties, like forming with no metals, burning impossibly hot, or collapsing into black holes without a trace, be the universe's version of beta testing? Even their distribution feels oddly optimized, as if someone tweaked the variables to maximize efficiency before settling on today's more balanced stellar recipes. Here's where it gets eerie. Some physicists argue that if our universe were programmed, its most extreme objects, like those first stars, would expose the seams. Their unexplained traits, why that massive, why that short-lived, might be artifacts of the code, like finding pixels in a supposedly perfect VR world. But before we spiral into existential dread, there's a counterpoint. Nature loves extremes without needing a programmer. The early universe was a lab of raw physics, and those stars might simply reflect conditions we've never witnessed since. Still, the simulation angle offers a wild thought experiment. If we ever decode all the mysteries of cosmic dawn, will the answers feel too elegant? Like equations polished by trial runs in some higher reality. Whether you buy the idea or laugh it off, the first stars force us to confront how little we grasp about reality's foundations. Maybe they're natural wonders, or maybe they're the universe's way of winking at us, hinting that the rules we cling to aren't the whole story. And honestly, that delicious uncertainty is why science never gets old. So there we have it, 30 mind-bending theories about the universe's first stars, each more astonishing than the last. From dark matter midwives shaping stellar births to stars so massive they collapsed into black holes without a trace, the early cosmos was anything but ordinary. We've explored how these ancient giants might have been powered by dark matter annihilation, forged in hidden dimensions, or even left behind mysterious free-floating planets. Yet for all we've uncovered, the biggest revelation might just be how much we don't know. Think about it, we're piecing together the story of cosmic dawn using faint whispers of light, ghostly echoes of explosions, and mathematical models that constantly surprise us. Every answer leads to new questions. Did the first stars die quietly or in gamma-ray bursts visible across the universe? Are there remnants hiding in plain sight, or did they vanish into higher dimensions? The search is far from over. That's the beauty of astronomy. Every discovery peels back another layer of the universe's secrets, and you get to be part of it. So tell us in the comments which theory blew your mind the most, the dark matter stars, the quasi-star black hole hybrids, or something even wilder. And if you love diving into cosmic mysteries like this, don't forget to subscribe for more journeys to the edge of what we understand. The universe has endless stories left to tell, and we're just getting started.